Welcome to Machine Learning Tutorial Part 2. My name is Richard Kirschner with the Simplilearn team. That is www.simplilearn.com. Get certified, get ahead. Today in our second tutorial we're going to cover k-means and linear regression, along with going over the quiz questions we had during our first tutorial. What's in it for you? We're going to cover clustering. What is clustering? K-means clustering, which is one of the most common used clustering tools out there, including a flowchart to understand k-means clustering and how it functions. And then we'll do an actual Python live demo on clustering of cars based on brands. Then we're going to cover logistic regression. What is logistic regression? Logistic regression curve and sigmoid function. And then we'll do another Python code demo to classify a tumor as malignant or benign based on features. And let's start with clustering. Suppose we have a pile of books of different genres. Now we divide them into different groups like fiction, horror, education, and as we can see from this young lady, she definitely is into heavy horror. You can just tell by those eyes and the maple Canadian leaf on her shirt. But we have fiction, horror, and education, and we want to go ahead and divide our books up. Well, organizing objects into groups based on similarity is clustering. And in this case, as we're looking at the books, we're talking about clustering things with known categories. But you can also use it to explore data. So you might not know the categories, you just know that you need to divide it up in some way to conquer the data and to organize it better. But in this case, we're going to be looking at clustering in specific categories. And let's just take a deeper look at that. We're going to use k-means clustering. K-means clustering is probably the most commonly used clustering tool in the machine learning library. K-means clustering is an example of unsupervised learning. If you remember from our previous thing, it is used when you have unlabeled data. So we don't know the answer yet. We have a bunch of data that we want to cluster into different groups. Define clusters in the data based on feature similarity. So we've introduced a couple terms here. We've already talked about unsupervised learning and unlabeled data. So we don't know the answer yet. We're just going to group stuff together and see if we can find an answer of how things connect. We've also introduced feature similarity, features being different features of the data. Now with books, we can easily see fiction and horror and history books, but a lot of times with data, some of that information isn't so easy to see right when we first look at it. And so k-means is one of those tools where we can start finding things that connect, that match with each other. Suppose we have these data points and want to assign them into a cluster. Now when I look at these data points, I would probably group them into two clusters just by looking at them. I'd say two of these group of data kind of come together. But in k-means, we pick k-clusters and assign random centroids to clusters, where the k-clusters represents two different clusters. We pick k-clusters and assign random centroids to the clusters, then we compute distance from objects to the centroids. Now we form new clusters based on minimum distances and calculate the centroids. So we figure out what the best distance is for the centroid, then we move the centroid and recalculate those distances. Repeat previous two steps iteratively till the cluster centroids stop changing their positions and become static. Repeat previous two steps iteratively till the cluster centroids stop changing and the positions become static. Once the clusters become static, then k-means clustering algorithm is said to be converged. And there's another term we see throughout machine learning is converged. That means whatever math we're using to figure out the answer has come to a solution, or it's converged on an answer. Shall we see the flowchart to understand? Make a little bit more sense by putting it into a nice easy step-by-step. So we start, we choose k, we'll look at the elbow method in just a moment. We assign random centroids to clusters, and sometimes you pick the centroids, because you might look at the data in a graph and say, oh, these are probably the central points. Then we compute the distance from the objects to the centroids. We take that and we form new clusters based on minimum distance and calculate their centroids. Then we compute the distance from objects to the new centroids. And then we go back and repeat those last two steps. We calculate the distances. So as we're doing it, it brings into the new centroid, and then we move the centroid around and we figure out which objects are closest to each centroid. So the objects can switch from one centroid to the other as the centroids are moved around. And we continue that until it is converged. Let's see an example of this. Suppose we have this data set of 7 individuals and their score on two topics, A and B. So here's our subject. In this case, referring to the person taking the test. And then we have subject A, where we see what they've scored on their first subject, and we have subject B, and we can see what they score on the second subject. Now let's take two farthest apart points as initial cluster centroids. Now remember, we talked about selecting them randomly, or we can also just put them in different points and pick the furthest one apart so they move together. Either one works okay, depending on what kind of data you're working on and what you know about it. So we took the two furthest points, 1 and 1, and 5 and 7. And now let's take the two farthest apart points as initial cluster centroids. Each point is then assigned to the closest cluster with respect to the distance from the centroids. So we take each one of these points in there, we measure that distance, and you can see that if we measured each of those distances, and you use the Pythagorean theorem for a triangle in this case, because you know the x and the y, and you can figure out the diagonal line from that. Or you can just take a ruler and put it on your monitor. That'd be kind of silly, but it would work if you're just eyeballing it. You can see how they naturally come together in certain areas. Now we again calculate the centroids of each cluster. So cluster 1 and then cluster 2, and we look at each individual dot. There's 1, 2, 3, we're in one cluster. The centroid then moves over. It becomes 1.8, 2.3. So remember, it was at 1 and 1? Well, the very center of the data we're looking at would put it at the roughly 2.2, but 1.8 and 2.3. And the second one, if we wanted to make the overall mean vector, the average vector of all the different distances to that centroid, we come up with 4, 1 and 5, 4. So we've now moved the centroids. We compare each individual's distance to its own cluster, mean, and to that of the opposite cluster, and we find, we can build a nice chart on here, that as we move that centroid around, we now have a new different kind of clustering of groups, and using Euclidean distance between the points and the mean, we get the same formula. You see new formulas coming up. So we have our individual dots, distance to the mean centroid of the cluster, and distance to the mean centroid of the cluster. Only individual 3 is nearer to the mean of the opposite cluster, cluster 2, than its own cluster 1. And you can see here in the diagram where we've kind of circled that 1 in the middle. So when we've moved the centroids of the clusters over, one of the points shifted to the other cluster because it's closer to that group of individuals. Thus, individual 3 is relocated to cluster 2, resulting in a new partition. And we regenerate all those numbers of how close they are to the different clusters. For the new clusters, we will find the actual cluster centroids. So now we move the centroids over. And you can see that we've now formed two very distinct clusters on here. On comparing the distance of each individual's distance to its own cluster mean and to that of the opposite cluster, we find that the data points are stable. Hence, we have our final clusters. Now, if you remember, I brought up a concept earlier, k-mean on the k-means algorithm. Choosing the right value of k will help in less number of iterations. And to find the appropriate number of clusters in a data set, we use the elbow method. And within sum of squares, WSS, is defined as the sum of the squared distance between each member of the cluster and its centroid. And so you see what we've done here is we have the number of clusters. And as you do the same k-means algorithm over the different clusters, and you calculate what that centroid looks like, and you find the optimal, you can actually find the optimal number of clusters using the elbow of the graph, is called as the elbow method. And on this, we guessed at 2 just by looking at the data. But as you can see, the slope, you actually just look for right there where the elbow is in the slope, and you have a clear answer that we want 2 different, to start with k-means equals 2. A lot of times people end up computing k-means equals 2, 3, 4, 5 until they find the value which fits on the elbow joint. Sometimes you can just look at the data, and if you're really good with that specific domain, remember domain, I mentioned that last time, you'll know that where to pick those numbers or where to start guessing at what that k value is. So let's take this, and we're going to use a use case using k-means clustering to cluster cars into brands using parameters such as horsepower, cubic inches, make, year, etc. So we're going to use the dataset cars data, having information about 3 brands of cars, Toyota, Honda, and Nissan. We'll go back to my favorite tool, the Anaconda Navigator with the Jupyter Notebook. And let's go ahead and flip over to our Jupyter Notebook. And in our Jupyter Notebook, I'm going to go ahead and just paste the basic code that we usually start a lot of these off with. We're not going to go too much into this code because we've already discussed NumPy, we've already discussed Matplotlib, and pandas. NumPy being the number array, pandas being the pandas data frame, and Matplot for the graphing. And don't forget, since if you're using the Jupyter Notebook, you do need the Matplot library inline so that it plots everything on the screen. If you're using a different Python editor, then you probably don't need that because it'll have a pop-up window on your computer. And we'll go ahead and run this just to load our libraries and our setup into here. The next step is, of course, to look at our data, which I've already opened up in a spreadsheet. And you can see here we have the miles per gallon, cylinders, cubic inches, horsepower, weight pounds, how heavy it is, time it takes to get to 60. My card is probably on this one at about 80 or 90. What year it is. So this is, you can actually see this is kind of older cars, and then the brand, Toyota, Honda, Nissan. So the different cars are coming from all the way from 1971, if we scroll down, to the 80s. We have between the 70s and 80s a number of cars that they've put out. And let's, when we come back here, we're going to do importing the data. So we'll go ahead and do dataset equals. And we'll use pandas to read this in, and it's from a CSV file. Remember, you can always post this in the comments and request the data files for these, either in the comments here on the YouTube video or go to simplylearn.com and request that. The cars CSV, I put it in the same folder as the code that I've stored. So my Python code is stored in the same folder, so I don't have to put the full path. If you store them in different folders, you do have to change this and double check your name variables. And we'll go ahead and run this, and we've chosen dataset arbitrarily because it's a dataset we're importing, and we've now imported our cars CSV into the dataset. As you know, you have to prep the data, so we're going to create the X data. This is the one that we're going to try to figure out what's going on with. And then there's a number of ways to do this, but we'll do it in a simple loop so you can actually see what's going on. So we'll do for I in x.columns. So we're going to go through each of the columns, and a lot of times it's important. I'll make lists of the columns and do this because I might remove certain columns, or there might be columns that I want to be processed differently. But for this, we can go ahead and take x of I, and we want to go fill NA, and that's a pandas command. But the question is, what are we going to fill the missing data with? We definitely don't want to just put in a number that doesn't actually mean something. And so one of the tricks you can do with this is we can take x of I, and then in addition to that, we want to go ahead and turn this into an integer, because a lot of these are integers. So we'll go ahead and keep it integers. And we add the bracket here. And a lot of editors will do this. They'll think that you're closing one bracket. Make sure you get that second bracket in there if it's a double bracket. That's always something that happens regularly. So once we have our integer of x of I, this is going to fill in any missing data with the average. And I was so busy closing one set of brackets, I forgot that the mean also has brackets in there for the pandas. So we can see here we're going to fill in all the data with the average value for that column. So if there's missing data, it's in the average of the data it does have. And then once we've done that, we'll go ahead and loop through it again and just check and see to make sure everything is filled in correctly. And we'll print, and then we take x is null, and this returns a set of the null value, or the how many lines are null, and we'll just sum that up to see what that looks like. And so when I run this, and so with the x, what we want to do is we want to remove the last column because it had the models. That's what we're trying to see, if we can cluster these things and figure out the models. There is so many different ways to sort the x out. For one, we could take the x, and we could go dataset, our variable we're using, and use the iLocation, one of the features that's in pandas. And we could take that and then take all the rows and all but the last column of the dataset. And at this time we could do values. We just convert it to values. So that's one way to do this. And if let me just put this down here and print x, it's a capital X we chose, and I run this, you can see it's just the values. We could also take out the values, and it's not going to return anything because there's no values connected to it. What I like to do with this is, instead of doing the iLocation, which does integers, more common is to come in here and we have our data set, and we're going to do dataset dot columns. And remember, that lists all the columns. So if I come in here, let me just mark that as red, and I print dataset.columns. You can see that I have my index here. I have my MPG, cylinders, everything, including the brand, which we don't want. So the way to get rid of the brand would be to do data columns of everything but the last one, -1. So now if I print this, you'll see the brand disappears. And so I can actually just take dataset columns minus 1, and I'll put it right in here for the columns we're going to look at. And let's unmark this, and unmark this. And now if I do an x.head, I now have a new data frame, and you can see right here we have all the different columns except for the brand at the end of the year. And it turns out when you start playing with the data set, you're going to get an error later on, and it'll say cannot convert string to float value. And that's because for some reason these things, the way they recorded them, must have been recorded as strings. So we have a neat feature in here on pandas to convert. And it is simply convert objects. And for this we're going to do convert underscore numeric equals true. And yes, I did have to go look that up. I don't have it memorized, the convert numeric in there. If I'm working with a lot of these things, I remember them, but depending on where I'm at, what I'm doing, I usually have to look it up. And we run that. Oops, I must have missed something in here. Let me double check my spelling. And when I double check my spelling, you'll see I missed the first underscore in the convert objects. And when I run this, it now has everything converted into a numeric value, because that's what we're going to be working with, is numeric values down here. And the next part is that we need to go through the data and eliminate null values. Most people, when they're doing small amounts, working with small data pools, discover afterwards that they have a null value and they have to go back and do this. So, be aware, whenever we're formatting this data, things are going to pop up, and sometimes you go backwards to fix it. And that's fine. That's just part of exploring the data and understanding what you have. And I should have done this earlier, but let me go ahead and increase the size of my window one notch. There we go. Easier to see. So we'll do for I in working with x.columns. We'll page through all the columns. And we want to take x of I, and we're going to change that, and we're going to alter it. And so with this, we want to go ahead and fill in x of I. Pandas has the fill NA, and that just fills in any non-existent missing data. And we'll put my brackets up, and there's a lot of different ways to fill this data. If you have a really large data set, some people just void out that data and then look at it later in a separate exploration of data. One of the tricks we can do is we can take our column and we can find the means. And the means is in our quotation marks. So when we take the columns, we're going to fill in the non-existing one with the means. The problem is that returns a decimal float. So some of these aren't decimals. Certainly, we need to be a little careful of doing this, but for this example, we're just going to fill it in with the integer version of this. It keeps it on par with the other data that isn't a decimal point. And then what we also want to do is we want to double check. A lot of times you do this first part first to double check, then you do the fill, and then you do it again just to make sure you did it right. So we're going to go through and test for missing data. And one of the ways you can do that is simply go in here and take our x of I column. So it's going to go through the x of I column. It says is null. So it's going to return any place there's a null value. It actually goes through all the rows of each column is null. And then we want to go ahead and sum that. So we take that and we add the sum value. And these are all pandas. So is null is a panda command, and so is sum. And if we go through that and we go ahead and run it, and we go ahead and take and run that, you'll see that all the columns have 0 null values. So we've now tested and double checked, and our data is nice and clean. We have no null values. Everything is now a number value. We turned it into numeric. And we've removed the last column in our data. And at this point, we're actually going to start using the elbow method to find the optimal number of clusters. So we're now actually getting into the sklearn part, the k-means clustering on here. I guess we'll go ahead and zoom it up one more notch so you can see what I'm typing in here. And then from sklearn, sklearn cluster, we're going to import k-means. I always forget to capitalize the K and the M when I do this. So it's capital K, capital M, K-means. And we'll go ahead and create a array, WCSS equals, we'll make it an empty array. If you remember from the elbow method from our slide, within the sum of squares, WSS is defined as the sum of square distance between each member of the cluster and its centroid. So we're looking at that change in differences as far as a square distance. And we're going to run this over a number of k-mean values. In fact, let's go for I in range, we'll do 11 of them. Range 0 of 11. And the first thing we're going to do is we're going to create the actual, we'll do it all lowercase. And so we're going to create this object from the k-means that we just imported. And the variable that we want to put into this is in clusters. And we're going to set that equals to I. That's the most important one because we're looking at how increasing the number of clusters changes our answer. There are a lot of settings to the k-means. Our guys in the back did a great job just kind of playing with some of them. The most common ones that you see in a lot of stuff is how you init your k-means. So we have k-means plus plus. This is just a tool to let the model itself be smart how it picks its centroids to start with, its initial centroids. We only want to iterate no more than 300 times. We have a max iteration we put in there. We have the nth init, the random state equals 0. You really don't need to worry too much about these when you're first learning this. As you start digging in deeper, you start finding that these are shortcuts that will speed up the process as far as the setup. But the big one that we're working with is the in clusters equals I. So we're going to literally train our k-means 11 times. We're going to do this process 11 times. And if you're working with big data, you know the first thing you do is you run a small sample of the data so you can test all your stuff on it. And you can already see the problem that if I'm going to iterate through a terabyte of data 11 times, and then the k-means itself is iterating through the data multiple times, that's a heck of a process. So you got to be a little careful with this. A lot of times, though, you can find your elbow, using the elbow method, find your optimal number on a sample of data, especially if you're working with larger data sources. So we want to go ahead and take our k-means and we're just going to fit it. If you're looking at any of the sklearn, very common, you fit your model. And if you remember correctly, our variable we're using is the capital X. And once we fit this value, we go back to the array we made, and we want to go ahead and just append that value on the end. And it's not the actual fit we're pinning in there, it's when it generates the value you're looking for is inertia. So k-means.inertia will pull that specific value out that we need. And let's get a visual on this. We'll do our PLT plot, and what we're plotting here is first the x-axis, which is range 0, 11, so that will generate a nice little plot there, and the WCSS for our y-axis. It's always nice to give our plot a title, and let's see, we'll just give it the elbow method for the title, and let's get some labels. So let's go ahead and do PLT X label, and what we'll do number of clusters for that, and PLT Y label, and for that we can do, oops, there we go, WCSS, since that's what we're doing on the plot on there. And finally we want to go ahead and display our graph, which is simply PLT dot show. There we go. And because we have it set to inline, it'll appear inline. Hopefully I didn't make a type error on there. And you can see we get a very nice graph. You can see a very nice elbow joint there at 2, and again right around 3 and 4, and then after that there's not very much. Now, as a data scientist, if I was looking at this, I would do either 3 or 4, and I'd actually try both of them to see what the output looked like. And they've already tried this in the back, so we're just going to use 3 as a setup on here. And let's go ahead and see what that looks like when we actually use this to show the different kinds of cars. And so let's go ahead and apply the k-means to the cars data set. And basically we're going to copy the code that we looped through up above, where k-means equals k-means number of clusters, and we're just going to set the number of clusters to 3. since that's what we're going to look for. And you could do 3 and 4 on this and graph them just to see how they come up differently. It'd be kind of curious to look at that. But for this, we're just going to set it to 3. Go ahead and create our own variable, y k-means, for our answers. And we're going to set that equal to, whoops, a double equal there, to k-means. But we're not going to do a fit. We're going to do a fit predict is the setup you want to use. And when you're using untrained models, you'll see a slightly different, because usually you see fit and then you see just the predict. But we want to both fit and predict the k-means on this. And that's fit underscore predict, and then our capital X is the data we're working with. And before we plot this data, we're going to do a little pandas trick. We're going to take our X value and we're going to set X as matrix. So we're converting this into a nice rows and columns kind of setup, but we're going to have columns equals none, so it's just going to be a matrix of data in here. And let's go ahead and run that. A little warning. You'll see these warnings pop up because things are always being updated. So there's like minor changes in the versions and future versions. Instead of matrix, now it's more common to set it at .values instead of doing as matrix. But as matrix works just fine for right now. You'll want to update that later on. But let's go ahead and dive in and plot this and see what that looks like. And before we dive into plotting this data, I always like to take a look and see what I am plotting. So let's take a look at y k-means. I'm just going to print that out down here. And we see we have an array of answers. We have 2, 1, 0, 2, 1, 2. So it's clustering these different rows of data based on the 3 different spaces it thinks it's going to be. And then let's go ahead and print X and see what we have for X. And we'll see that X is an array, it's a matrix, so we have our different values in the array. And what we're going to do, it's very hard to plot all the different values in the array. So we're only going to be looking at the first 2, or positions 0 and 1. And if you were doing a full presentation in front of the board meeting, you might actually do a little different and dig a little deeper into the different aspects, because this is all the different columns we looked at. But we'll only look at columns 1 and 2 for this to make it easy. So let's go ahead and clear this data out of here, and let's bring up our plot. And we're going to do a scatter plot here. So PLT scatter, and this looks a little complicated, so let's explain what's going on with this. We're going to take the X values, and we're only interested in y of k-means equals 0, the first cluster. Okay? And then we're going to take value 0 for the x-axis, and then we're going to do the same thing here. We're only interested in k-means equals 0, but we're going to take the second column. So we're only looking at the first 2 columns in our answer, or in the data. And then the guys in the back played with this a little bit to make it pretty. And they discovered that it looks good if it has a size equals 100. That's the size of the dots. We're going to use red for this one. And when they were looking at the data and what came out, it was definitely the Toyota on this. We're just going to go ahead and label it Toyota. Again, that's something you'd really have to explore in here as far as playing with those numbers and see what looks good. We'll go ahead and hit enter in there. And I'm just going to paste in the next 2 lines, which is the next 2 cars. And this is our Nissan and Honda. And you'll see with our scatter plot, we're now looking at where y underscore k means equals 1. And we want the 0 column, and y k means equals 2. Again, we're looking at just the first 2 columns, 0 and 1. And each of these rows then corresponds to Nissan and Honda. And I'll go ahead and hit enter on there. And finally, let's take a look and put the centroids on there. Again, we're going to do a scatter plot. And on the centroids, you can just pull that from our k-means, the model we created, dot cluster centers, and we're going to just do all of them in the first number and all of them in the second number, which is 0, 1, because you always start with 0 and 1. And then they were playing with the size and everything to make it look good. We'll do a size of 300. We're going to make the color yellow, and we'll label them. It's always good to have some good labels, centroids. And then we do want to do a title, PLT title, and pop up there. PLT title, because you always want to make your graphs look pretty, and we'll call it clusters of car make. And one of the features of the plot library is you can add a legend. It'll automatically bring in it since we've already labeled the different aspects of the legend with Toyota, Nissan, and Honda. And finally, we want to go ahead and show, so we can actually see it. And remember, it's inline, so if you're using a different editor that's not the Jupyter Notebook, you'll get a pop-up of this. And you should have a nice set of clusters here. So we can look at this and we have clusters of Honda in green, Toyota in red, Nissan in purple. And you can see where they put the centroids to separate them. Now, when we're looking at this, we can also plot a lot of other different data on here because we only looked at the first two columns. This is just column 1 and 2, or 0, 1 as you label them in computer scripting. But you can see here we have nice clusters of car make, and we were able to pull out the data. And you can see how just these two columns form very distinct clusters of data. So if you were exploring new data, you might take a look and say, well, what makes these different? Almost going in reverse, you start looking at the data and pulling apart the columns to find out why is the first group set up the way it is. Maybe you're doing loans and you want to go, well, why is this group not defaulting on their loans? And why is the last group defaulting on their loans? And why is the middle group 50% defaulting on their bank loans? And you start finding ways to manipulate the data and pull out the answers you want. So now that you've seen how to use k-mean for clustering, let's move on to the next topic. Now let's look into logistic regression. The logistic regression algorithm is the simplest classification algorithm used for binary or multi-classification problems. And we can see we have our little girl from Canada who's into horror books is back. That's actually really scary when you think about that with those big eyes. In the previous tutorial, we learned about linear regression, dependent and independent variables. So, to brush up, y equals mx plus c. Very basic algebraic function of y and x. The dependent variable is the target class variable we are going to predict. The independent variables, x1 all the way up to xn, are the features or attributes we're going to use to predict the target class. We know what a linear regression looks like, but using the graph we cannot divide the outcome into categories. It's really hard to categorize 1.5, 3.6, 9.8. For example, a linear regression graph can tell us that with increase in number of hours studied, the marks of a student will increase, but it will not tell us whether the student will pass or not. In such cases where we need the output as categorical value, we will use logistic regression. And for that we're going to use the sigmoid function. So you can see here we have our marks, 0 to 100, number of hours studied. That's going to be what they're comparing it to in this example. And we usually form a line that says y equals mx plus c. And when we use the sigmoid function, we have p equals 1 over 1 plus e to the minus y. It generates a sigmoid curve. And so you can see right here when you take the ln, which is the natural logarithm. I always thought it should be nl, not ln. That's just the inverse of e, or e to the minus y. And so when we do this, we get ln of p over 1 minus p equals m times x plus c. That's the sigmoid curve function we're looking for. And we can zoom in on the function, and you'll see that the function, as it derives, goes to 1 or to 0, depending on what your x value is. And the probability, if it's greater than 0.5, the value is automatically rounded off to 1, indicating that the student will pass. So if they're doing a certain amount of studying, they will probably pass. Then you have a threshold value at the 0.5. It automatically puts that right in the middle usually. And your probability, if it's less than 0.5, the value rounded off to 0, indicating the student will fail. So if they're not studying very hard, they're probably going to fail. This, of course, is ignoring the outliers of that one student who's just a natural genius and doesn't need any studying to memorize everything. That's not me, unfortunately. I have to study hard to learn new stuff. Problem statement. To classify whether a tumor is malignant or benign. And this is actually one of my favorite data sets to play with because it has so many features, and when you look at them, you really are hard to understand. You can't just look at them and know the answer. So it gives you a chance to kind of dive into what data looks like when you aren't able to understand the specific domain of the data. But I also want you to remind you that in the domain of medicine, if I told you that my probability was really good at classified things at, say, 90% or 95%, and I'm classifying whether you're going to have a malignant or a benign tumor, I'm guessing that you're going to go get it tested anyways. So you got to remember the domain we're working with. So why would you want to do that if you know you're just going to go get a biopsy because, you know, it's that serious? This is like an all or nothing. Just referencing the domain, it's important. It might help the doctor know where to look just by understanding what kind of tumor it is. So it might help them or aid them in something they missed from before. So let's go ahead and dive into the code, and I'll come back to the domain part of it in just a minute. So use case, and we're going to do our normal imports here, where we're importing NumPy, Pandas, Seaborn, the Matplotlib library, and we're going to do Matplotlib library inline since I'm going to switch over to Anaconda. So let's go ahead and flip over there and get this started. So I've opened up a new window in my Anaconda Jupyter Notebook. And by the way, Jupyter Notebook, you don't have to use Anaconda for the Jupyter Notebook. I just love the interface and all the tools that Anaconda brings. So we got our import NumPy as in P for our NumPy number array. We have our Pandas PD. We're going to bring in Seaborn to help us with our graphs as SNS. So many really nice tools in both Seaborn and Matplotlib library. Then we'll do our Matplotlib library.pyplot as PLT, and then of course we want to let it know to do it in line. And let's go ahead and just run that so it's all set up. And we're just going to call our data, not creative today, equals PD, and this happens to be in a CSV file. So we'll use the pd.read_CSV, and I happen to name the file, I renamed it, data for p2.csv. You can, of course, write in the comments below the YouTube and request for the data set itself, or go to the Simplilearn website, and we'll be happy to supply that for you. And let's just open up the data before we go any further, and let's just see what it looks like in a spreadsheet. So when I pop it open in a local spreadsheet, and this is just a CSV file, comma separated variables, we have an ID, so I guess they categorize this for reference or what ID, which test was done. The diagnosis, M for malignant, B for B9, so there's two different options on there. And that's what we're going to try to predict is the M and B and test it. And then we have like the radius mean or average, the texture average, perimeter mean, area mean, smoothness. I don't know about you, but unless you're a doctor in the field, most of the stuff, I mean, you can guess what concave means just by the term concave, but I really wouldn't know what that means in the measurements they're taking. So they have all kinds of stuff like how smooth it is, the symmetry, and these are all float values. We can just page through them real quick, and you'll see there's, I believe, 36 if I remember correctly in this one. So there's a lot of different values they take and all these measurements they take when they go in there and they take a look at the different growth, the tumorous growth. So back in our data, and I put this in the same folder as the code. So I saved this code in that folder. Obviously, if you have it in a different location, you want to put the full path in there. And we'll just do Pandas first 5 lines of data with the data.head. When we run that, we can see that we have pretty much what we just looked at. We have an ID, we have a diagnosis. If we go all the way across, you'll see all the different columns coming across displayed nicely for our data. And while we're exploring the data, our Seaborn, which we referenced as SNS, makes it very easy to go in here and do a joint plot. You'll notice very similar to, because it is sitting on top of the plot library, so the joint plot does a lot of work for us. And we're just going to look at the first 2 columns that we're interested in, the radius mean and the texture mean. We'll just look at those 2 columns. And data equals data. So that tells it which 2 columns we're plotting and that we're going to use the data that we pulled in. And let's just run that. And it generates a really nice graph on here. And there's all kinds of cool things on this graph to look at. I mean, we have the texture mean and the radius mean, obviously the axes. You can also see and one of the cool things on here is you can also see the histogram. They show that for the radius mean. Where is the most common radius mean come up and where the most common texture is. So we're looking at on each growth its average texture and on each radius its average radius on there. It gets a little confusing because we're talking about the individual object's average, and then we can also look over here and see the histogram showing us the median or how common each measurement is. And that's only 2 columns, so let's dig a little deeper into Seaborn. They also have a heat map. And if you're not familiar with heat maps, a heat map just means it's in color. That's all that means. Heat map I guess the original ones were plotting heat density on something, and so ever since then it's just called a heat map. And we're going to take our data and get our corresponding numbers to put that into the heat map. And that's simply data.corr for that. That's a pandas expression. So remember, we're working in a pandas data frame, so that's one of the cool tools in pandas for our data. And let's just pull that information into a heat map and see what that looks like. And you'll see that we're now looking at all the different features. We have our ID, we have our texture, we have our area, our compactness, concave points. And if you look down the middle of this chart, diagonal, going from the upper left to bottom right, it's all white. That's because when you compare texture to texture, they're identical. So they're 100%, or in this case, a perfect 1 in their correspondence. And you'll see that when you look at, say, area, or right below it, it has almost a black on there when you compare it to texture. So these have almost no corresponding data. They don't really form a linear graph or something that you can look at and say how connected they are. They're very scattered data. This is really just a really nice graph to get a quick look at your data. It doesn't so much change what you do, but it changes verifying. So when you get an answer or something like that, or you start looking at some of these individual pieces, you might go, hey, that doesn't match. According to showing our heat map, this should not correlate with each other. And if it is, you're going to have to start asking, well, why? What's going on? What else is coming in there? But it does show some really cool information on here. I mean, we can see from the ID, there's no real one feature that just says, if you go across the top line, that lights up. There's no one feature that says, hey, if the area is a certain size, then it's going to be benign or malignant. It says there's some that sort of add up. And that's a big hint in the data that we're trying to ID this, whether it's malignant or benign. That's a big hint to us as data scientists to go, okay, we can't solve this with any one feature. It's going to be something that includes all the features, or many of the different features, to come up with a solution for it. And while we're exploring the data, let's explore one more area, and let's look at data.isNull. We want to check for null values in our data. If you remember from earlier in this tutorial, we did it a little differently where we added stuff up and summed them up. You can actually, with pandas, do it really quickly, data.isNull, and sum it, and it's going to go across all the columns. So when I run this, you're going to see all the columns come up with no null data. So we've just to rehash these last few steps, we've done a lot of exploration. We have looked at the first two columns and seen how they plot with the seaborne, with a joint plot which shows both the histogram and the data plotted on the XY coordinates. And obviously you can do that more in detail with different columns and see how they plot together. And then we took and did the seaborne heat map, the SNS heat map of the data. And you can see right here where it did a nice job showing us some bright spots where stuff correlates with each other and forms a very nice combination or points of scattering points. And you can also see areas that don't. And then finally we went ahead and checked the data. Is the data null value? Do we have any missing data in there? Very important step because it'll crash later on. If you forget to do this step, it will remind you when you get that nice error code that says null values. Okay, so not a big deal if you miss it, but it's no fun having to go back when you're in a huge process and you've missed this step and now you're 10 steps later and you got to go remember where you were pulling the data in. So we need to go ahead and pull out our X and our Y. So we just put that down here. And we'll set the X equal to, and there's a lot of different options here. Certainly we could do X equals all the columns except for the first two, because if you remember the first two is the ID and the diagnosis. So that certainly would be an option. But what we're going to do is we're actually going to focus on the worst radius, the worst texture, parameter, area, smoothness, compactness, and so on. One of the reasons to start dividing your data up when you're looking at this information is sometimes the data will be the same data coming in. So if I have two measurements coming into my model, it might overweigh them. It might overpower the other measurements because it's basically taking that information in twice. That's a little bit past the scope of this tutorial. What I want you to take away from this, though, is that we are dividing the data up into pieces, and our team in the back went ahead and said, hey, let's just look at the worst. So I'm going to create an array And you'll see this array, radius worst, texture worst, perimeter worst. We've just taken the worst of the worst, and I'm just going to put that in my X. So this X is still a pandas data frame, but it's just those columns. And our Y, if you remember correctly, is going to be, oops, hold on one second. It's not X, it's data. There we go. So X equals data, and then it's a list of the different columns, the worst of the worst. And if we're going to take that, then we have to have our answer for our Y, for the stuff we know. And if you remember correctly, we're just going to be looking at the diagnosis. That's all we care about is what is it diagnosed? Is it benign or malignant? And since it's a single column, we can just do diagnosis. Oh, I forgot to put the brackets. There we go. Okay. So it's just diagnosis on there. And we can also real quickly do like X dot head if you want to see what that looks like. And Y dot head. And run this. And you'll see it only does the last one. I forgot about that if you don't do print. You can see that the Y dot head is just MMM because the first ones are all malignant. And if I run this, the X dot head is just the first 5 values of radius worst, texture worst, parameter worst, area worst, and so on. I'll go ahead and take that out. So moving down to the next step, we've built our 2 data sets, our answer and then the features we want to look at. In data science, it's very important to test your model. So we do that by splitting the data. And from sklearn model selection, we're going to import train test split. So we're going to split it into 2 groups. There are so many ways to do this. I noticed in one of the more modern ways, they actually split it into 3 groups, and then you model each group and test it against the other groups. So you have all kinds of, and there's reasons for that, which is past the scope of this, and for this particular example isn't necessary. For this, we're just going to split it into 2 groups, one to train our data and one to test our data. And the sklearn model selection, we have train test split. You could write your own quick code to do this where you just randomly divide the data up into 2 groups, but they do it for us nicely. And we can actually do it in one statement with this, where we're going to generate 4 variables, capital X train, capital X test. So we have our training data we're going to use to fit the model, and then we need something to test it. And then we have our Y train, so we're going to train the answer, and then we have our test. So this is the stuff we want to see how good it did on our model. And we'll go ahead and take our train test split that we just imported. And we're going to do X and our Y, our 2 different data that's going in for our split. And then the guys in the back came up and wanted us to go ahead and use a test size equals 0.3. That's test underscore size. Random state, it's always nice to kind of switch your random state around, but not that important. What this means is that the test size is we're going to take 30% of the data and we're going to put that into our test variables, our Y test and our X test. And we're going to do 70% into the X train and the Y train. So we're going to use 70% of the data to train our model and 30% to test it. Let's go ahead and run that and load those up. So now we have all our stuff split up and all our data ready to go. And now we get to the actual logistics part. We're actually going to create our model. So let's go ahead and bring that in from sklearn. We're going to bring in our linear model and we're going to import logistic regression. That's the actual model we're using. And this, we'll call it log model. Oops, there we go, model. And let's just set this equal to our logistic regression that we just imported. So now we have a variable log model set to that class for us to use. And with most of the models in the sklearn, we just need to go ahead and do a fit on there. And we use our X train that we separated out with our Y train. Now let's go ahead and run this. So once we've run this, we'll have a model that fits this data, that 70% of our training data. And of course it prints this out that tells us all the different variables that you can set on there. There's a lot of different choices you can make. But for what we're doing, we're just going to let all the defaults sit. We don't really need to mess with those on this particular example. And there's nothing in here that really stands out as super important until you start fine-tuning it. But for what we're doing, the basics will work just fine. And then we need to go ahead and test out our model. Is it working? So let's create a variable yPredict. And this is going to be equal to our log model. And we want to do a predict. Again, very standard format for the sklearn library is taking your model and doing a predict on it. And we're going to test yPredict against the yTest. So we want to know what the model thinks it's going to be. That's what our yPredict is. And with that, we want the capital X test. So we have our train set and our test set, and now we're going to do our yPredict. And let's go ahead and run that. And if we print yPredict, let me go ahead and run that. You'll see it comes up and it prints a nice array of B and M for benign and malignant for all the different test data we put in there. So it does pretty good. We're not sure exactly how good it does, but we can see that it actually works and is functional. It was very easy to create. You'll always discover with our data science that as you explore this, you spend a significant amount of time prepping your data and making sure your data coming in is good. There's a saying, good data in, good answers out. Bad data in, bad answers out. That's only half the thing. That's only half of it. Selecting your models becomes the next part as far as how good your models are. And then, of course, fine-tuning it depending on what model you're using. So we come in here, we want to know how good this came out. So we have our yPredict here, logModel.predictXtest. So for deciding how good our model is, we're going to go from the sklearn.metrics, we're going to import classification report. And that just reports how good our model is doing, and then we're going to feed it the model data. And let's just print this out. And we'll take our classification report, and we're going to put into there our test, our actual data. So this is what we actually know is true. And our prediction, what our model predicted for that data on the test side. And let's run that and see what that does. So we pull that up, you'll see that we have a precision for benign and malignant, B and M. And we have a precision of 93 and 91, a total of 92. So it's kind of the average between these two of 92. There's all kinds of different information on here. Your F1 score, your recall, your support coming through on this. And for this, I'll go ahead and just flip back to our slides that they put together for describing it. And so here we're going to look at the precision using the classification report. And you see this is the same printout I had up above. Some of the numbers might be different because it does randomly pick out which data we're using. So this model is able to predict the type of tumor with 91% accuracy. So when we look back here, you'll see where we have benign and malignant. It actually is 92 coming up here. But we're looking at about a 92, 91% precision. And remember, I reminded you about domain. So when we're talking about the domain of a medical domain with a very catastrophic outcome, at 91 or 92% precision, you're still going to go in there and have somebody do a biopsy on it. Very different than if you're investing money and there's a 92% chance you're going to earn 10% and 8% chance you're going to lose 8%, you're probably going to bet the money. Because at that odds, it's pretty good that you'll make some money. And in the long run, you do that enough, you definitely will make money. And also with this domain, I've actually seen them use this to identify different forms of cancer. That's one of the things that they're starting to use these models for. Because then it helps the doctor know what to investigate. So that wraps up this section. We're going to go in there and let's discuss the answer to the quiz asked in Machine Learning Tutorial Part 1. Can you tell what's happening in the following cases? Grouping documents into different categories based on the topic and content of each document. This is an example of clustering where k-means clustering can be used to group the documents by topics using bag of words approach. So if you've gotten in there that you're looking for clustering, and hopefully you had at least one or two examples like k-means that are used for clustering different things, then give yourself a 2 thumbs up. B. Identifying handwritten digits in images correctly. This is an example of classification. The traditional approach to solving this would be to extract digit-dependent features like curvature of different digits, etc., and then use a classifier like SVM to distinguish between images. Again, if you got the fact that it's a classification example, give yourself a thumb up, and if you're able to go, hey, let's use SVM or another model for this, give yourself those 2 thumbs up on it. C. Behavior of a website indicating that the site is not working as designed. This is an example of anomaly detection. In this case, the algorithm learns what is normal and what is not normal, usually by observing the logs of the website. Give yourself a thumbs up if you got that one. And just for a bonus, can you think of another example of anomaly detection? One of the ones I use it for in my own business is detecting anomalies in stock markets. Stock markets are very fickle and they behave very erratic. So finding those erratic areas and then finding ways to track down why they're erratic. Was something released in social media? Was something released? You can see where knowing where that anomaly is can help you to figure out what the answer is to it in another area. D. Predicting salary of an individual based on his or her years of experience. This is an example of regression. This problem can be mathematically defined as a function between independent, years of experience, and dependent variables, salary of an individual. And if you guessed that this was a regression model, give yourself a thumbs up. And if you're able to remember that it is between independent and dependent variables and that terms, give yourself 2 thumbs up. Summary. So to wrap it up, we went over what is k-means. And we went through also the chart of choosing your elbow method and assigning a random centroid to the clusters, computing the distance, and then going in there and figuring out what the minimum centroids is and computing the distance and going through that loop until it gets the perfect centroid. And we looked into the elbow method to choose k based on running our clusters across a number of variables and finding the best location for that. We did a nice example of clustering cars with k-means, even though we only looked at the first 2 columns to make it simple and easy to graph. You can easily extrapolate that and look at all the different columns and see how they all fit together. And we looked at what is logistic regression. We discussed the sigmoid function, what is logistic regression, and then we went into an example of classifying tumors with logistics. I hope you enjoyed part 2 of machine learning. Thank you for joining us today. For more information, visit www.simplylearn.com. Again, my name is Richard Kirschner, a member of the Simplylearn team. Get certified, get ahead. If you have any questions or comments, feel free to write those down below the YouTube video or visit us at simplylearn.com. We'll be happy to supply you with the data sets or other information as requested.
Hi there, if you like this video, subscribe to the Simplylearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.